If your app talks to 3 model providers, your real problem is not prompts, it's routing, budgets, and failover. And LiteLLM gives you one control plane for all 3. This is the setup you'll be able to run after this, which routes chat requests under a daily budget and rate limit, while auto-falling back across providers and tracking spend. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams start by calling a single model directly. That works until costs spike or one provider has a hiccup. Then, you scramble to rewire clients, add retries, or throttle users. LiteLLM Proxy solves that operational mess by acting as a single control plane. It sits between your app and multiple providers and enforces per-key budgets, rate limits, and fallback rules. Success looks like predictable monthly spend, graceful slowdowns, and automatic retries to cheaper or available models. At a high level, think of LiteLLM Proxy as a smart router with a wallet and a clock. The router decides which provider to use. The wallet tracks spend and stops requests when a budget hits 0. The clock enforces rate limits. This gives you predictable behavior under load and during provider failures. The trade-off is one more network hop and the need to configure policies up front. We will build a tiny demo in Python. You will see a quick latency check, mint a scoped key with a small budget, trigger rate limiting, exercise automatic model fallbacks, and then check key level spend. Each step shows one aspect of routing, limits, budgets, and failover, so the whole system feels concrete before you deploy it. Now, we will send a test request through the proxy. This snippet sends a minimal chat request through the LiteLLM Proxy and measures latency. It creates an OpenAI client configured with base URL pointing at the local proxy and uses a simple messages list containing a single user ping. The call client.chat.completions.create invokes the proxy's OpenAI-compatible /v1 chat completions endpoint with a small max tokens cap to keep it fast. A timer around the request captures end-to-end latency and converts it to milliseconds. If you increase max tokens, responses usually take longer and may cost more. The printed latency helps validate connectivity and gives a first performance baseline through the proxy. Next, we will mint a scoped API key with deliberate limits. This example uses the LiteLLM Proxy Admin API to mint a scoped key with budget and rate limits. It posts to /key_generate with a JSON body that sets max budget to 0.5 USD, RPM limit to 1 request per minute, and TPM limit to 2,000 tokens per minute. The admin key in the authorization header authenticates this management action. The response returns a new user-scoped key captured in user key for subsequent requests. Lowering RPM limit makes the key throttle sooner, while raising TPM limit accommodates larger prompts without token errors. The printed key tail gives a short identifier to track this key during the rest of the demo. Now we will stress the new key with a quick burst to show throttling. This code sends a small burst of 2 chat requests through LiteLLM Proxy using the newly generated limited key. It posts to the OpenAI-compatible /v1 chat completions endpoint with a tiny max tokens to keep responses quick. The loop collects response statuses and increments rate limited whenever a 429 too many requests is returned. Because RPM limit is 1, the second immediate request is likely throttled by the proxy. If you increase RPM limit, this counter tends to drop to 0. Decreasing it makes throttling more aggressive. The printed count confirms that proxy-side rate limiting is active for this key. Next, we will force a model miss and watch the proxy fall back. This snippet demonstrates automatic failover using the LiteLLM Proxy's Fallbacks field. It intentionally requests a non-existent model named bad.model and supplies a fallbacks list containing GPT-4o Mini. The proxy attempts the primary model, detects the error, then transparently retries with the next model in the list. The response JSON's model field reveals which model actually served the request, captured in the variable used. Reordering or expanding the fallbacks list changes which provider is tried next and can influence latency and cost. The printed model name confirms that the request succeeded by routing to a fallback. Finally, we will inspect the key to see how spend is tracked. This snippet queries LiteLLM Proxy for key-level spend so you can watch budget burn. It posts to the admin endpoint /key info, authenticating with the admin key and passing the user key to inspect. The proxy returns fields such as max budget and spend, which the code reads into the dictionary info. It then computes the remaining budget by subtracting spend from max budget and rounds to 2 decimals for clarity. If you lower max budget in key creation, this remaining balance will shrink faster under the same traffic. The printed remaining budget confirms that spend tracking is working and enforces financial guardrails. In a real project, this same flow maps directly to production traffic. Your service talks to the local proxy, not to each provider. The proxy applies the key limits, routes requests to the cheapest healthy provider, and stops traffic if the budget is exhausted. That pattern works for web apps, chatbots, and any multi-provider LLM stack. Recap what it is. A control plane that routes requests, enforces budgets and rate limits, and handles fallbacks. When to use it. When you need predictable spend, graceful degradation, or multi-provider resilience. One caveat. You add one network hop and a configuration step, so test latency and policy settings before wide rollout. Wrap, punch. Next, tune the RPM limit and TPM limit for realistic traffic to find the sweet spot between user experience and cost. If practical AI engineering helps, subscribe and watch the AI engineering videos.